Have you ever wondered if a growing population eventually, stabilizes? Or maybe if a cooling object ever reaches room temperature exactly? Well, to answer that, we're going to need to look far, far away. We need to look to infinity. Welcome back to The Explainer, future doctors, engineers, and mathematicians. Are you ready for a brand new mathematical thrill ride? Because today, we're asking the biggest question of all. What exactly happens at the end of time? Or, well, rather, at the end of the x-axis. Let's go. Okay, let's just dive right into this. Here at Mr. Math, we've tackled some pretty wild concepts together. But today we're venturing out into the vastness of the absolute unknown. We are going to master the infinite horizon. Part 1. The concept. What is infinity? So in our previous explainers, we looked at what happens to a function as x approaches a specific finite number, like 2 or 0. But today, x is going on a journey to the very end of the universe. It's becoming larger and larger without bound. It literally never stops. Now, notice what happens to our function during this infinite journey. Imagine a curve just flying off to the right. If that function, f of x, eventually settles down and essentially hugs a specific horizontal line as it goes way out to infinity, we call that line a horizontal asymptote. Think of it kind of like an airplane climbing up into the sky and eventually hitting its cruising altitude where it just levels out. Part 2. The golden rule. The rule of reciprocals. Listen up, because I'm about to give you the single most powerful algebraic tool for this entire topic. Seriously, if you remember just one thing from today's explainer, make it this. Ready? Here it is. The limit as x approaches infinity of 1 over x to the power of n equals 0. Let's make this intuitive. Think about a pizza. If you take one single pizza and divide it among a million people, everyone gets almost nothing, right? Just a microscopic crumb. Now, what if you divide it among a billion people? Even less. As the denominator grows infinitely large, the overall fraction just dies. It goes straight to 0. This simple rule is the master key to unlocking almost every single limit at infinity. But wait, hold on a second. Pause right here and really think about this question. We know from algebra that a function can never, ever cross a vertical asymptote. That's a hard, infinite wall. But what about a horizontal asymptote? Can a function cross it? Can it, wiggle around, dip below, pop above, and then settle down? Take a mental guess. Got it? Well, the answer is absolutely yes. A function can definitely cross its horizontal asymptote, sometimes even multiple times, before it finally exhausts its energy and just hugs the line out at infinity. Which brings us to part 3, algebraic rescue, dividing the giants. So what happens when infinity clashes with infinity? Our trusted calculus author, James Stewart, actually gives us a brilliant systematic strategy for resolving a fight between two massive polynomials as they both race toward infinity. Take a look at this rational function battle. We've got a quadratic polynomial in the numerator and another quadratic in the denominator. As x gets infinitely large, the top blows up to infinity and the bottom blows up to infinity. It's a massive tug of war. How can we possibly figure out the winner? Well, here is Stewart's 3-step strategy to rescue us. Step 1. Identify the highest power of x in the denominator. Step 2. Divide every single term, top and bottom, by that exact power. And step 3. Apply our golden rule of reciprocals. So looking back at our denominator, the highest power of x is x squared. That means x squared is our divisor. Let's execute this strategy. And wow, this brilliantly illustrates the transformation. When we divide the numerator by x squared, the 3x squared becomes just 3. The negative x becomes minus 1 over x, and the negative 2 becomes minus 2 over x squared. We do the exact same thing to the denominator. Now, step 3. We apply the golden rule. As x approaches infinity, any term with an x in the bottom, remember, that's our single pizza divided by a billion people, goes straight to 0. So minus 1 over x, 0. Minus 2 over x squared, 0. The 4 over x and 1 over x squared both vanish entirely into 0. And boom, look at what we're left with. All those small fractional terms are completely wiped out, and literally only the lead coefficients remain. Our final answer, giving us a perfectly clean, beautiful horizontal asymptote, is 3/5. The polynomials basically fought to a standstill, settling perfectly at 0.6. Part 4, Mr. Math's pro tip. Watch the square roots. Okay, I really need you to pay close attention right now because we're shifting to a critical warning about a super common exam trap. It catches countless students off guard every single semester.
The crucial point here is understanding how square roots interact with negative numbers. You've got to remember that the square root of x squared isn't always just x. It's actually technically the absolute value of x. If you're traveling toward positive infinity, great, no problem, the square root of x squared is just x. But if you're traveling to negative infinity, x is a negative number. That means the absolute value of x is negative x. The directional sign literally flips.
Let's see how this actually traps you. Check out this problem. We are taking the limit as x approaches negative infinity. Now, you might just naturally divide the bottom by x and the top by the square root of x squared and assume they cancel cleanly. But because we're heading to negative infinity, when you pull that x out from the square root, it drags a negative sign with it. Failing to check the direction here will trap you with the exact wrong sign on your final exam. Always, always check your map before you travel to infinity. The ultimate challenge. Test your limits. Okay, heroes, you've mastered the golden rule, you've divided the giants, and you've survived the tricky square root trap. Now it's time for the final boss battle. Here is your challenge. Evaluate the limit as x approaches infinity of the square root of the quantity x squared plus 1 minus x. Now, be super careful here. This is what we call an infinity minus infinity situation. Both terms grow infinitely large, so you can't just subtract them and boldly say it's 0. They are fiercely fighting each other. Here's your hint. You absolutely must use the algebraic rationalization trick, multiplying by the conjugate, to turn this difference into a fraction, and then use our dividing the giant strategy. Can you find the answer? And with that, congratulations! You've officially mastered the infinite horizon. If you're following the Stewart calculus order with us, our very next stop is the incredible world of derivatives. Don't forget to leave your solution to the ultimate challenge in the comments below. I really want to see if you got 0, 1, or something completely different. Ultimately, does the math just break, or is there actual order at the end of time? Let me know what you think, and I'll see you in the next mathematical thrill ride.